Hello everyone and welcome back. Okay, so last time we talked about strain. It was the intensity of these deformations within a body. Now, let's look at our bar. I mean, we've been looking at bars a whole lot. We're going to come back to a bar this time. And we're going to look at the deformation of a bar due to an axial load. So, we have a perfectly perpendicular surface here. We apply that load. It has some original length and it has some sort of elongations. Now, for those cases where the strain is uniform across the members, we've spread this force out, and it's like a pressure more than just a single force. The strain can be easily calculated. As just another note, if I go somewhere inside of my member, like away from the surface, even if I had a big old point load that wouldn't actually affect things, it smooths out once you get away from the surface. Okay, and what that strain looks like is the following. This one right here, epsilon, and this is the average strain. It's going to be equal to the elongation over the original length. Elongation over the original length. Now, the units of strain are dimensionless. We have length over length right here. Units would cancel. We have meters on top, meters on the bottom. Doesn't matter. The units will cancel. However, to make writing small values easier, this unitless dimension is often marked by a strain right here. This sigma, again, sorry, not sigma, this epsilon. And we refer to that as strains. Now, strains are never more than 1. It's always a fraction, so it'll be like 0.5 strains. And also, it's usually tiny, like microstrains are much more normal than anything else. So what you'll see for units a lot of times, you'll see a unit that is not a real unit. This strain right here is unitless. It's just an easier way of talking about it than just saying really tiny fractions. And so we might say, well, if it's stretched, 1 millimeter over a original length of 1,000 millimeters, well, that is tiny. That's 0.001. And that's it. That's all you would get. And so to make it easier to talk about, well, I can say, okay, well, that was 1 millistrain. And you just remember that that's 0.001 and that there's actually no units. Okay, now what about abnormal strain at a particular point? Now for those cases, you're going to have to calculate the derivative. You're going to take the derivative of the deformation over the elongation. We start with a big one, which is the average, and we move our way over here to get that strain at a particular point. We rarely have to do this. This does not come up often, and you'll be much more using this all the time. But just in case, if you have to find at a particular point and you have all those functions, there it is. Here it is. We're going to take that derivative. Now, one common case where the strain might not be uniform is in the bending of a beam. If we bend it, the top and bottom have opposite stresses and strains. You can kind of see that if you have a bar that's like this, and I bend it in half, well, you can see the top has gotten longer, the bottom has gotten compressed and shorter, and so obviously they would have different strains, and that's where we would need to use things like this. But by that point, we'll have even simpler ways of looking at it. Yes, I know it's be further along, and you're like, how can it be simpler if it's further along? It will be simpler. We'll have done so many problems by that point that you'll just be like, I know all of this. I believe in you. Okay, now how do you measure strain experimentally? Well, we use something that's called a strain gauge. It looks like this. It's got a plastic backing, it's got this metal foil, which is a sensing grid, and it's got these alignment marks which help you figure out how you're putting it on your particular part. And finally, there's these solder tabs which will attach to some electrodes which will go off to your machine. And as it stretches, what's going to happen is that the resistance in this metal foil will get greater or less. And that will cause the current going through it and the voltage to change. And so there will be some amazing calibration you'll use to start, given by the company. And then based on how the voltage and current has changed, you can then figure out what the strain is from that strain gauge. Maybe one of these days we'll have a real lab in this class, and I will actually bring these in, and we can have a terrifying time of trying to get these to work. It's a lot of fun, but it's also very difficult to get them on there perfectly. So with that, we'll stop here, and next time I'll actually jump into a couple examples of calculating strain. And I will say this, the group problems for this section, they are very, very involved and very difficult. So I highly suggest that you watch those. Don't just skip over them, because they go into some great detail about how to use our normal strain equations in a somewhat more realistic scenario. Well, thanks for listening, and I'll see you all next time. Bye-bye.